Hello students, welcome to EPG Pathshala. I am Dr. Varun Vyas from Department of Physics and Astrophysics, University of Delhi. Today we are going to talk on module Schottky barrier capacitance, impurity concentration under the paper characterization of materials part 1. After completing this module, a student will be able to understand the following topics: metal semiconductor or MS junction, the critical parameters Schottky barrier height, Schottky Mott rule and Fermi level pinning, rectifying properties, impurity concentrations, that is doping, and its effects. The electric current flowing across a metal semiconductor interface is generally a nonlinear with respect to the applied bias voltage. As the result of a discontinuity in the energy scale of electronic states responsible for conduction in the two materials. Here in figure 1, a band diagram of the interface is sketched to show this discontinuity. Delocalized electron states around the Fermi level Fl are responsible for electrical conduction in metals. Drawn on the left, but these states are not coupled to any delocalized electronic states in the semiconductor, drawn on the right. The set of electronic states responsible for electrical conduction in the semiconductor depends on the type of doping of the semiconductor. In case of type semiconductor, the electron present close to the conduction band minimum, that is CBM, contribute to the electrical conduction. Whereas in p-type semiconductors, the holes available near the valence band maximum, that is VBM, contribute to the electrical conduction. Because of the presence of fundamental band gap, the lowest lying states for n-type semiconductor that can communicate with electrons in the metal are now at energy level phi Bn raised to power 0 above the Fermi level as shown in the figure. When semiconductor interface is formed, this energy offset phi naught, also known as n-type Schottky barrier height, causes a potential energy barrier which acts as a rectifier such that electrons can readily flow from semiconductor to metal, while electrons flow in the opposite direction is difficult. When the semiconductor is in contact with the metal is doped p-type, the energy gap between the Fermi level and the VBN, marked as phi naught Bp, becomes the energy barrier, that is p-type Schottky barrier height, that governs the whole transport across the metal semiconductor interface. Since the flow of the current across a metal semiconductor interface exponentially depends on the magnitude of the Schottky barrier height at common applied voltages, the Schottky barrier height is vital characteristics of a metal semiconductor interface that decides its electrical characteristics. Physics of formation. Metal semiconductor junction. A junction is made up of a close contact of a metal and a semiconductor is termed as a metal semiconductor junction and is the earliest semiconductor device which was practically used. Both rectifying and non-rectifying type of contacts can be prepared from a metal semiconductor junction. Rectifying types MS junctions comprise a Schottky barrier. and the resulting device is termed as a Schottky diode. On the other hand, a non-rectifying type junction is termed as ohmic contact. Another type of contact is a rectifying type semiconductor junction, that is SS junction, which is extensively used semiconductor device. It is also termed as PN junction. MS junction is integral to the operation of all semiconductor devices. Ohmic contact is desirable when electrical charge is required to be easily transported between the active region of a transistor and the external circuit. In contrast, the Schottky contact is required in Schottky diodes, transistors, MS field effect transistors, etc. The critical parameter, Schottky barrier height. The Schottky barrier height is denoted as phi b of a junction decides whether a particular MS junction is ohmic or Schottky. When Schottky barrier height is high enough to cause the phi b much larger than the thermal energy kT, the semiconductor gets depleted near the metal and behaves as a Schottky barrier. In contrast, when Schottky barrier height is low, there is no depletion of semiconductor and an ohmic contact is formed between the metal and the semiconductor. For both p-type and n-type semiconductors, Schottky barrier height is described differently, such that for a p-type semiconductor, it is measured from the valence band edge, whereas from n-type, it is measured from conduction band edge. Near the junction, the alignment of bands of semiconductor does not depend on the doping level of the semiconductor. Thus, the heights of n p-type Schottky barriers are interrelated by the following relation. Here, phi b raised to power n plus phi b raised to power p is equals to Eg. This is represented as equation 1. Here, Eg represents the band gap of the semiconductor. Generally, the height of the Schottky barrier is not constant across the interface. Rather, it varies at its surface. Schottky Mott rule and Fermi level pinning. Schottky Mott rule is an approximation which can be used to predict the height of the Schottky barrier. According to this rule, the height of the Schottky barrier formed at the MS junction is approximately equal to the difference in the metalwork function and electron affinity of the semiconductor, where both quantities are measured in vacuum. That is, phi b raised to power n is equivalent to phi metal minus psi of the semiconductor. This is represented as equation 2. The idea behind this model considers bringing together two material in vacuum and is similar to the formation of semiconductor junctions via Anderson's rule. The Schottky-Mott rule is obeyed by different semiconductors to varying degrees. Even though the Schottky-Mott model could correctly predict the band bending phenomena in semiconductor, experimental results demonstrate that it could not yield Schottky barrier height precisely. It suffered a mechanism termed as Fermi level pinning, wherein some points of the band gap having DOS locked or pinned to the Fermi level, thereby making the height of the Schottky barrier nearly independent of the work function of the metal. Here, phi b is equivalent to 1 by 2 into E band gap. Here, E band gap represents the semiconductor band gap, and the above equation is represented as equation 3. John Barden observed in 1947 that Fermi level pinning occurs naturally in semiconductor if it has chargeable states near the interface having energies in the energy gap of the semiconductor. Such chargeable states are either created as a result of direct chemical bonding between the metals and the semiconductor in brackets and are termed as metal induced gap states or present surface of the semiconductor vacuum interface. That is, they are termed as the surface states. These extremely dense surface states trap most of the charges donated by the metal, thereby the shielding the semiconductor from the metal. Consequently, the alignment of bands in the semiconductor corresponds to a location relative to these surface states, which are already pinned to the Fermi level because of their high densities and becomes insensitive to the metal. Many commercial semiconductors suffer from Fermi pinning phenomena, causing difficulties in device fabrication. Examples of these semiconductors include silicon, germanium, gallium arsenide, etc. Since the valence band in the p-type germanium is pinned to the Fermi level of the metal, most of the metals from ohmic contact with p-type germanium and Schottky barrier with n-type germanium. This problem can be alleviated by including additional processes, for example, addition of insulating intermediate layer to unpin the bands, gallium germanium nitride insulation is usually used in case of germanium. Schottky motrule is schematically shown in figure 3a as the two different materials, silver and n-type silicon in this case, approach each other. Semiconductors bend so as to match the work function of silicon with that of silver. This bending of bands is attained even after the contact. This model envisages a very small Schottky barrier for silver and n-type silicon junction, resulting in an ohmic contact between them. Figure 3b shows the Fermi level pinning phenomena due to the metal-induced gap states. The surface states cause band gap bending in silicon, therefore making the contact the bands again bend such that the work function of both the materials is matched. However, on contact formation, the bending alters depending upon the nature of the chemical bond between the silver and n-type silicon. Rectifying properties. All MS junction do not produce a rectifying Schottky barrier, as a MS junction can conduct current in both directions with equal ease, thereby forming an ohmic contact. This can be attributed to the Schottky barrier being too low at the MS junction. When the Schottky barrier is considered high, a depletion region is formed in semiconductor at the semiconductor MS interface. This results in high resistance at the interface when applied bias voltage is low. However, when large voltage is applied across the junction, laws of thermionic emission and the fixed Schottky barrier relative to the Fermi level of metal govern the flow of electric current across the junction. Forward bias. Under forward bias, there are many thermally excited electrons in the semiconductor which can cross over the barrier. The passage of electrons over the barrier without any electrons returning back results in the flow of electric current in the opposite direction. When bias is increased, this current also increases. However, at very high bias, the voltages, the current is limited by the series resistance of the semiconductor. Reverse bias. As shown here in figure 5, In reverse bias, the barrier is too high for thermally excited electrons to enter the conduction band from the metal. Under reverse bias, very less number of thermally excited electrons in metal have enough energy to cross the barrier. Thus, a small leakage current flows. This leakage current is not constant but gradually increases with reverse bias voltage, owing to a weak barrier lowering, same as the vacuum Schottky effect. However, when reverse bias is increased to higher values, the depletion region breaks down. Minority carrier injection. When Schottky barrier is very high, such that it forms a considerable fraction of the semiconductor's band gap, the forward bias current may instead be carried underneath the Schottky barrier as minority carriers in the semiconductor. However, when Schottky barrier is increased such that it is same as the band gap of the semiconductor, the forward bias current is carried by minority carrier injections. This is shown in figure 6 with the white arrow indicating the injection of an electron hole in the valence band of the semiconductor. Calculation of Schottky barrier height. Schottky barrier height, that is SBH, is generally calculated from the transport measurements of Schottky barrier diodes processed or patterns on non-degenerate semiconductors. Current voltage, that is IV, and the capacitance voltage, that is CV, are important methods of determining SBH. Both these techniques presume that the barrier height being studied is uniform. In IV method, injection current is recorded with varying applied voltage. From logarithmic plot of the forward bias current, the saturation current, and the ideality factor are obtained. By thumb ionic emission theory, diode saturation current and SBH are linked as ISAT is equals to A into A star into T square exponential to minus FBN divided by KBT. This is represented as equation 4. Here, A star is Richardson constant for a semiconductor and A is the diode area. An accurate information about the total diode area is prerequisite for determining Schottky barrier height by IV measurements. For diodes with the unknown area, the Schottky barrier height may still be known by examining the temperature dependence of junction current, where junction current is measured at varying temperature, set a fixed bias voltage that is lying in the linear portion of the constant temperature IV plot. A temperature dependent saturation current is the most preferred investigation since this current is the forward component of the total current under zero bias condition. The logarithm of I star t minus 2 t raised to power minus 2 can be plotted in the Richardson plot as a function of inverse temperature t raised to power minus 1. The Schottky barrier height is then the sum of the calculated activation energy from the plot and the fixed applied bias used in the experiment. In CV measurements, the high frequency, that is greater than 500 kHz capacitance of uniformly doped Schottky diode is recorded with varying bias voltage. This experiment is conducted in the reverse bias to minimize the effect of in-phase current on the measurements. By plotting the inverse of the junction capacitance against the applied bias, flat band voltage can be determined by linear exploitation of voltage axis. For instance, for N-type semiconductor, the barrier height can be obtained as FBN is equals to EVHI plus EVN plus KBT. This is represented as equation 5. Here, EVHI is built-in voltage and EVN is the difference between the Fermi level and the conduction band minimum for a neutral semiconductor. Impurity concentration. The properties of an intrinsic semiconductor may be modified by introducing impurities, that is doping. The resulting material is called extrinsic semiconductor. The amount of the dopants or the impurities influence a material's charge carrying concentration. Under thermal equilibrium, the number of electrons and holes are equal in any intrinsic semiconductor. That is, N is equals to P is equals to Ni. If extrinsic semiconductor with low doping, the above thermal equilibrium relation changes to N naught into P naught is equals to Ni square, where N naught and P naught are the respective concentrations of electrons and holes, and Ni is equals to intrinsic carry concentration of the semiconductor, and it varies across different materials and also depends on temperature. Increase in the doping increases the carry concentration, thereby enhancing the conductivity. Excessively doped or degenerate semiconductors exhibit conductivities comparable to the metals and find applications in integrated circuits as replacement for metals. Subscript plus minus signs represent the relative doping concentrations in semiconductors. That is, N plus shows a heavily doped N-type semiconductor and P minus denotes very lightly doped P-type semiconductor. Effect of band structure. Electrons donating impurities generate additional states close to conduction band, whereas the electron deficient or acceptors impurities generate states close to valence band. This band gap between these energy states and closest energy band is termed as dopant site bonding energy, or EB, and is usually small. Due to small values of EB, the room temperature thermally ionizes almost all the dopant atoms and creates free charge carriers in conduction or valence band. Dopants can further cause shift in energy bands with respect to Fermi level. Energy band of a dopant having highest concentration lies closest to the Fermi level. As Fermi level is constant for a system in thermal equilibrium, the piling multiple layers of materials having varying properties results in novel properties caused by band bending. Most common example is the p-n junction, which has unique properties generated by band bending, which is a consequence of joining the bands in contact region of p and n-type materials. So students, let us now summarize what we have learned in this module. In this module, we look into the characteristics of the Schottky barrier, which is a potential energy barrier for electrons formed at metal semiconductor junction. We studied about the Schottky molecule and barrier rectifying properties. With the help of illustrations, one could understand about the role of conduction bands at the metal semiconductor junctions. In the end, we learn about the effects of dopants, that is, impurities, on the energy bands with respect to the Fermi levels. Thank you.